by the time we get done with this chapter, it'll be a week from. I think we're scheduled to have this homework due a week from Friday or something like that. I don't know what it is. Let's take a look. Right now, chapter 10 is due the 15th, which I guess is actually this. Oh, no. That's next week, right? Next Friday?
Next Friday.
Yeah. So by the time we're done with this chapter, we'll have spent almost 3 weeks on it. Why they don't just build it into 2 chapters, I don't know, but they don't. So, or maybe 3 chapters. Because it really should be, but that's okay. We'll just spend 3 weeks on it. And then that'll give us a week before, let's see, week and a half before Thanksgiving, I guess. A week and a couple days to get started on the last couple of chapters on waves, or what is it? I don't know. Chapter 11. Oh, never mind. Chapter 11 is angular momentum. We'll do angular momentum before Thanksgiving. And then we'll probably do gravitation. We actually might do some static equilibrium as well, and before gravitation. But we'll probably get through. So this week we won't. This week we won't actually have a lab. We will still meet. Let's see. Will we have a lab? What have we done so far? We already did a lab for linear momentum and linear energy. Moments of inertia. We're gonna get to torque. We could actually do a lab this week with Tommaso. We should probably do it. We do a lab with him before he gets too bored. Not doing. We'll do it. He gets too bored doing a lab by himself, I guess. He's doing. What is he doing right now? Oh yeah, he's doing pressures. He's doing fluids. So if we can get through torque, if we can get through 10.6 by Wednesday, then we'll do a lab with Tommaso Thursday. Excuse me. And then the week after that he'll be doing the weeks after that he'll be doing more labs on his own with temperature and pressure. So we'll try to do a lab this week with him, and then after that we might do one lab for angular momentum, but after this there's not that many labs left to do. So for this class. So if you're going into chemistry or chemistry pretty much. If you're going into chemistry, usually you'll take 2 physics courses, and then you'll take a physical chemistry course, and then you will not do the physics of fluids. You will take a fluids class in chemistry of some kind. I don't know what they do. Actually, I don't even think they take a fluids class. I think they just don't mess with it really. I could be wrong, but anyway, you may learn some of that stuff later in chemistry, but you'll only take the 2 physics classes in physical chemistry, which will be in the chemistry department. If you go into engineering, it depends on what kind of engineering you go into. If you go into chemical engineering, it's the same. If you go into mechanical engineering or electrical engineering, you'll take a couple of more physics classes. You'll take a Physics 3 course, which is essentially fluids and wave dynamics, and fluids and thermal and wave dynamics, and then you'll take a modern physics course, which covers everything after 1905, everything after Einstein. So yeah, I don't know. I don't think chemical engineers take either of those other physics classes. I could be wrong, but I don't think so. I don't remember having chemical engineers in my classes. So depends on the school too. You know, different schools may do things differently. But I've never taught physics 3 here. We can offer it here if somebody wants to take it, but we've never done it. We actually may offer it next semester if Patrick decides he wants to take it. He's the first student I've had in quite a while that's been ready to take it by his second year, but we'll see. We shall see. Last time I taught a class like that was more than 10 years ago. It was at the school I taught at before here, so College of Eastern Utah. All right, so moment of inertia, rotational kinetic energy. We introduced you to the rotational kinetic energy, and the thing that I really want you to remember, two things that I really want you to remember from this. One is that as we were developing the rotational kinetic energy, we took, yes, I'm recording. As we were developing the rotational kinetic energy equation, we actually just took the original kinetic energy equation, translational or linear kinetic energy equation, and replaced V with omega r, which is just the relationship between rotational and tangential things, right? So when we did that, we ended up with this equation where we had a m times r squared in the middle of the equation instead of m. So we have a 1/2 times this thing omega squared instead of 1/2 mv squared. And this thing essentially is taking the place of our mass. But it includes not only mass, but where the mass is. So m times the position, or times the distance to the position, I guess is a better way to say it. And we decided to call this thing the moment of inertia, since it does determine how fast something is going to rotate, or how fast it's going to accelerate, or whatever, in rotational terms. So we call it the moment of inertia, or the rotational inertia, or whatever. Sometimes it's just called the moment. But our kinetic energy now becomes 1/2 I omega squared, where I is the moment. And this thing actually we will see a lot in rotational dynamics and rotational statics and other things. We will see this moment to take the place of mass in a lot of things. And we talked about the transfer of rotational kinetic energy into linear kinetic energy. You can use a spinning flywheel to turn your wheels, or to turn a generator and use the electricity to turn your wheels, or whatever. So here's the relationship. In the translational, you have mass, and the rotational, you have moment of inertia. Translational, you have 1/2 mv squared. Rotational, 1/2 I omega squared. So let's look at this example. We kind of got to this example at the end of class yesterday, but we didn't really have time to go over it. Here we have 6 particles in a system. They're all rotating around this axis down the middle, this y-axis, you could think of it as. And what we're going to do is we're going to calculate the moment of inertia of the system, where the rod that's holding these things together, whatever this blue thing is, has like negligible mass. It doesn't weigh much at all. And these individual masses here are the only things that contribute to the moment of inertia. Well, when we did our moment of inertia thing up here, we were considering a single mass at a single point, so a point mass. And that's exactly what these are. And we also considered that we could add a bunch of them together. And we've got a bunch of them, so we're going to add them together. So we're going to calculate the moment of inertia of each one of these things separately, and then add them all together to get the total moment of inertia. So here we see this. We have 0.2 kilograms. They're all of them are 0.2 kilograms, so we just multiply the mass out in front. And then we do the distances. We have two of them at 0.25 meters. We have two of them at 0.15 meters and two of them at 0.05 meters. So they're just adding them together. They're adding the r squareds together first. And then, since they have two of them, they do a multiplication thing here. You could also write this as 0.25 times 0.02, 0.25 times 0.02 plus 0.15 times 0.02 plus 0.15. These are all squareds, right? So times 0.02. You could make this in some really long thing too, but they just shorten it with some very simple arithmetic. But in the end, you get this total moment of inertia of 0.0035 kilograms meters squared. So that is the moment of inertia of the entire system, right? Now, in part B, they say if the two washers closest to the axis are removed, what is the moment of inertia of the remaining four? So the two that are closest are the 0.05 ones. So they take these off and do a calculation again. And look how much different it isn't. There's not much difference. Why? What's that? Yeah, the ones on the outside, the ones furthest away from the axis, are the ones that contribute the most, right? We determined that things that are far away from the axis of rotation are harder to get moving, have the most moment of inertia, so on and so forth. So the moment of those ones close in really just don't do much. They don't contribute much to the thing. Remember, it's distance squared, so the further you get away, it's not just a little bit more to the moment of inertia, it's a lot more, right? So the distance really does matter a lot. And the last thing is to calculate the kinetic energy of this at some particular angular velocity. And the angular velocity in this case is 5 times 2 pi radians per second. So it must be 5 revolutions per second or something like that. And so that becomes squared because it's I omega squared. There's the I that we got from part A. 1/2 I omega squared, 1.73 joules of kinetic energy stored in this rotational motion, or being used in this, or being manifest, I guess, in this rotational motion. Now you can calculate, using calculus, the moments of inertia of different shapes. And for very simple shapes, especially shapes that have symmetry, a lot of symmetry around their axes, it's quite, the answers come out quite cleanly. So for a hoop around an axis that it goes right through the middle of the hoop, it's just the same moment of inertia as a point particle. Why? Because this is just a bunch of point particles at the same distance from the center, right? If you added up a whole bunch of point particles infinitely close together, you would get a hoop of particles. So it's the same, I equals mr squared. However, if this thing all of a sudden has two different radiuses, in other words, if it has an inside radius and then has some thickness, and then an outside radius, this one here has no thickness. This one does. Then it's different. It becomes 1/2 m instead of r squared, it's r1 squared plus r2 squared. That's the math that comes out. So this is what they call an annular cylinder or a ring, right? What if it's a solid cylinder? Well, this one is actually 1/2 mr squared. It's like this one where r1 is 0, right? It's the same thing. What if we start spinning this thing around an axis that goes through the center of it? Instead of down the middle, down this cylindrical axis, it goes down the linear axis of it. So now this thing is going around like this. Well, that turns out that it's mr squared over 4 plus ml squared, well, L is the length, over 12. So the length of it actually contributes a little bit to this as well. It doesn't contribute maybe as much as this until the length gets really long. If the length starts to get long, then it starts to really contribute. But if it's shorter, not so much. Right? What if it's a thin rod? So it has pretty much no radius. In other words, the radius is 0. Well, of course, if the radius is 0, this part goes away, and it becomes ml squared over 2, 12. What if you do it around one end of it, so it's like swinging a bat around, right? Well, then it's actually ml squared over 3. That changes it a bit. If it's a solid sphere, 2/5 mr squared. If it's a hollow sphere, 2 mr squared over 3. If it's a hoop and it goes, and you have an axis that goes through the hoop from one side of the hoop to the other, so it's spinning around, I equals mr squared over 2. And then if you have a rectangular slab and you put an axis right through the center, it's this one here. So these are some of the more common shapes that have a good, that come out with a good formula for calculating the moment of inertia. Of course, you can do this for any shape at all. Any shape about any axis, you can calculate or measure the moment of inertia. But it doesn't always come out so cleanly. Sometimes it's really messy. And sometimes the only way to really do it is to spin the dumb thing and actually measure the moment of inertia, because it's just too complicated a shape or whatever. That happens very often in real life. So here is an example where we're going to spin 3, you could think of them as thin rods, right? Where the length of the propeller is much longer than the thickness of the propeller, and that's usually how you determine if the thickness is relevant. If the length is 10 times or more longer than the width of the propeller, or the width of the object, then usually you can start to say that the width doesn't matter so much. Not always, but usually. In this case, we're going to say that the width doesn't matter. It's just 4 meters long, has a mass of 50 kilograms. They're approximating them as thin rods. And we have 4 of them. And they're all rotating around their end. Now you could also think of this as 2 long rods rotating around their center, and it will come out the same way. Either way. So here's our, they want to calculate the rotational kinetic energy. We need to know what I is. They calculate omega from the revolutions per minute by just converting. And then the I, they do 4 times ml squared over 3. So they plug in the numbers, they get the moment of inertia, plug the moment of inertia into kinetic energy. You're simple. I mean, it's really done. It's really quite done right there, right? Here's your kinetic energy. But then they want to know the translational kinetic energy of the helicopter. So how fast is it going? 20 meters per second. Mass of the helicopter, 0.5. 2 times 10 to the 5th joules. So what you find out here is that of the kinetic energies, the spinning of the blades is far more kinetic energy than the actual movement of the helicopter. And this is very true. This is also true of airplanes in many cases. In airplanes, the propellers are spinning they have much more kinetic energy in them than the plane itself does. And what does that mean really for the passengers inside and for the helicopter itself? What it means is that first of all, it means that these modes of transportation are not very efficient, because you have a lot of energy going into these propellers, which do move the plane along, but they're also kind of like a waste of energy. They're the energy that is not directly part of the kinetic energy of the plane moving forward. They're just keeping the thing up, right? The other thing that it tells you is that you really don't want those propellers to get loose, right? The propellers on the airplane, if they get loose, they'll cut right through the plane like nothing else. And so it can be very dangerous. And if they fall to the ground, they can cause some serious damage on the ground. There's so much energy in them. The propellers on a helicopter, the little propeller on the back of the helicopter keeps the helicopter from spinning. If that one on the back stops working, the helicopter is toast, because it will start spinning like crazy. There's so much energy in those rotors. So it's really quite an interesting situation flying through the air. So here's another example where the energy in a boomerang. Anybody in here ever thrown a boomerang? No? Yeah? Actually got really quite good at it. My brother lived in Australia for a couple of years as a missionary, and then right before he went there, actually I visited Australia, but he sent me home a beautiful rosewood. I think it's called rosewood. There, it's this dark wood that they have in. No, it wasn't rosewood. What do they call it? I can't remember, but it's the wood that they use in Australia for making boomerangs, and it's a big boomerang. It was about this big, and I went out in the field and threw that thing for hours every day trying to figure it out. You know, I would just kind of go. Whoop, whoop. Finally, I figured out just the right angles and just the right whip of the hand to get it done, where it would go way out, and then it would go up in this huge arc, and then come back down and zip right down, and it would come right over my head. It was so fun. And now I can't find that. I think my brother has that again. I think somebody gave it back to him, which makes me sad because I wanted to keep it. But maybe I'll have to buy another one of these days. So anyway, here we have a boomerang. It has a velocity of 30 meters per second at an angle of 40 degrees, and the mass is 1 kilogram, rotating at 10 revolutions per second. Moment of inertia is I 1/12 ml squared. L is 0.7. What's the total energy of the boomerang when it leaves the hand? And how high does the boomerang go from the elevation of the hand, neglecting air resistance? So total energy of the boomerang when it leaves the hand. Moment of inertia, I 1/2 ml squared. 1/12 ml squared. The length, they've given you all those numbers, so you just calculate it. Angular velocity, calculate. And then the rotational kinetic energy, you can just calculate. Translational kinetic energy, you can calculate. The total energy of the boomerang, as it leaves your hand, then is the sum of those two kinetic energies. Now, conservation of mechanical energy is what we're going to use to calculate the height that it's going to go. Now, how do we figure that? Well, at the top of its motion, at the bottom of its motion, when he just throws it, everything is all kinetic energy. At the top of its motion, this thing is going to come to a rest in 2 dimensions. It's going to come to a rest in the y dimension and in the x dimension. It's not going to be moving either way. Well, let's see, is that what they're, because that's actually not true. No, so they're actually not going to say that. So they're actually doing it correctly. I thought they were going to do that. So it is actually, in the x direction, it's going to be going across this way, but it's not going to be going up or down anymore. So there's actually going to be 2 velocities, one in the x, one in the y, and one of them is going to go to 0, the other will not. At the maximum height, the x velocity will still be there. It will still have rotational kinetic energy because it will still be rotating, but the y velocity will be turned into potential energy, mgh. So this one's a little bit challenging because we need to split into x and y, preserve the x kinetic energy, it doesn't do anything, and only have the y kinetic energy. So we can actually do this. The y kinetic energy is going to be the sine of the 40 degrees here, right? That's going to tell us the y part, independently of the x part. So we'll go ahead and use the y part. And in truth, really, if you wanted to do this right, you'd want to do this in 3 dimensions, but that's okay. It gets a little more complicated. But, so we're going to use the fact that the going up of the boomerang is the y direction, 1/2 mvy squared equals mgh, and solve that for h. And then, of course, the vy is the 30 meters per second times the sine of 40 degrees. So this problem actually ends up being quite simple, but you do have to make sure that you recognize there's 3 kinds of kinetic energy at the beginning. One in the x direction, one in the y direction, both linear, and then the rotational kinetic energy. The thing never stops rotating, so that one stays with the problem the whole time. And of course, the x dimensional stays the same. When in truth, when you throw a boomerang, it always goes in a big loop. So you have not only x, what you have is you have x and y and z velocity. So you actually have to do it in 3 dimensions, but they don't give us that information. So. This is from my brother right here. Nuclear submarine propeller has a moment of inertia of 800 kilogram meters squared. Have you ever seen the propeller on a nuclear submarine? It's like 30 feet in diameter or more. They're humongous. So the Ohio class submarine is a nuclear submarine, and it has this propeller on it that is so incredibly huge. Made of bronze. Let's see if they actually have a photograph of one. Here we go. And it's really quite interesting, these propellers. So so this guy is, standing right here. That's the size of the propeller.
Oh, jeez.
Yeah. And they actually have a newer one. This is actually the newer one. No, that's the Kilo class. That's Russian. But they do have a newer one, I think is 6 blades. That's also Russian. Instead of the 5. But anyway, so these propellers are actually really quite interesting because they're designed not only to give a lot of thrust, but to be extremely efficient and for propellers, and also be extremely quiet. So the thing that causes noise behind these propellers is what's called cavitation. And that's what my brother's specialty is. That's what he did his research on at the university. And that's actually how he got his job, because the Navy was looking for somebody who knew, who had expertise in cavitation. What cavitation is when you move something through a fluid very, very quickly, it actually leaves little bubbles behind it. And the bubbles are actually vacuum bubbles. They're not air bubbles. And so these vacuum bubbles are filled with nothing, and eventually they collapse under the pressure of the water. When they collapse, they make a popping noise. And that popping noise is is cavitation. That popping noise is the sound you hear. That is the loudest sound that an Ohio-class submarine makes, is the popping of those little bubbles behind it. Everything else in the submarine is quieter than that, including, the dishes in the galley and the sailors walking up and down through the boat, and the talking, and the people's stereos, and the engine itself. The engine is actually super quiet. It uses a nuclear reactor to create electricity, and then the electricity is used to run the motors that turn the propeller. So, in fact, I think that's true. I don't know if they use a direct drive in Ohio. I don't think they do. But anyway, so it's a really, really quiet boat. In fact, once one of these things goes underwater, even the United States of America can't actually detect them, can't find out where they are. And the United States of America has sonar planted under every body of water on Earth. They have sonar speakers everywhere on Earth. So they know where everything is. They know where whales are. In fact, the U.S. Navy they kind of ended Greenpeace's big reign of political terror during the 80s and 90s, because when they started laying these sonar microphones under the water, they discovered that the whales that Greenpeace said were extinct were not extinct. They were just hiding. What's that? Well, they were actually hiding from whalers. Whales are actually fairly smart creatures, and so they learned to not go where the whalers are. And they actually had taught their calves that. And so, for example, it was thought that the blue whale was completely extinct, and it turns out it's not even close to extinct. It's just hiding. And the blue whale, of course, can go underwater for so long it can actually cross under the polar ice cap on the North Pole. And so they found a lot of them up at the North Pole, because the submarines spend a lot of time going under the North Pole. And all these hydrophones down there can actually detect whales, and they detect orcas and all these other things. And this is why you don't really hear about the extinction of the whales anymore, and that's why Greenpeace has lost a lot of their funding, because people were really excited about saving whales, and no, we don't need to save whales anymore. It's kind of funny, I think, personally. But anyway, turns out that nature's smarter than Greenpeace. Go figure. So that's an interesting one. All right. Oh, and actually oh, never mind. That's okay. One of the reasons they make that propeller so big, though, actually, the reason that I want to say that is because when you're talking about propellers, speed and energy is the thing that causes the cavitation sound. So the more energy the propeller has, the more the sound the cavitation makes. So it's the kinetic energy of the propeller. So kinetic energy of the propeller is 1/2 I omega squared, right? Well, if the I increases, that's not such a big deal. If the omega increases, that's a big deal because it's omega squared, right? So at first they thought, well, we'll make small propellers and we'll turn them faster and that will be better because it's actually more efficient to turn small propellers faster. However, they make more cavitation because their omega is really high. So they decided to go with big propellers that turn really quite slowly. Even though the edge of the propeller is moving quite quickly, the omega is fairly low. And so they cavitate less, and when they do cavitate, the cavitation is quieter. So all right, so a moment of inertia. We've already talked about what this is and how to calculate it in general, but there are some kind of tricks of the trade in calculating these things. You know, if you have two objects, like the masses on the end of a barbell, then you can just add those together and you just get 2mr squared for the masses on the end of the barbell. And if you want to add in the barbell itself, the actual bar, you can actually just add that in as well. So you look up the moment of inertia for a bar, and the moment of inertia for a bar is whatever it is, back in the last section. So we look at the moment of inertia for a bar around its center, right? And we're going to say that it has no radius, it's just a thin rod. It's pretty close for a barbell. So it's ml squared over 12. So you take the length of the bar, multiply it by the mass of the bar, divide by 12, and add that to the mr squareds for each of the masses on the end of the bar, and you get the total moment of inertia for the bar and the two masses. So moments of inertia are very much like mass, that once you've calculated, once you know what they are, you can just add them together for a system to get the total moment of inertia. However, there are some things that you have to be careful with because sometimes these things are not rotating around the center in the ways that we might think that they are. And what happens if we don't want to treat this, these masses out here as point masses? Because they're not points, they're disks. What if we want to treat it like a disk, right? Then we have to calculate it a little bit differently. And so we have some different ways that we can do that. And these different things all come from calculus in the end. And so we have to talk about calculus in the beginning. So let's talk about calculating the moment of inertia of a general shape object, like this blob of whatever. So there's this mass that has this whatever shape, and we're going to take each individual piece of the mass, and that we're gonna break it down into tiny little pieces. We're gonna call those the differential masses, dm, right? Just like we normally do. And then we're gonna get an integral instead of a summation. We're gonna have an integral where there is a distance r, or a displacement r from the center point, whatever we call the center point. We can choose that just as we choose. That can be completely up to us. And then arbitrary is the word, right? So you have whatever point you choose to be your center point, you have to use that throughout the problem that you're doing. And then you have your vector that goes r out to little dm. So there's an r associated with each little piece of mass, and it's r squared times every little piece of mass, and then you do an integral. And this is true for any shape. It doesn't matter what it is, a circle. There. Eventually, when you do this integral for a particular shape, the different r's in that shape will come out with the right numbers for a disk or for whatever else. But if it's some random shape, it's going to come out with some weird numbers out here, and that's fine too. So let's do the uniform thin rod. We just did this one. The uniform thin rod about its center was the length of the rod divided by 12 and times the mass, right? And Well, it was actually ml squared, wasn't it? Yeah, ml squared. So what we're going to do is we're going to break this into little pieces of mass. Now, because of the linear nature of this rod, each little piece of mass is going to have a length, a little piece of x, dx, right? And so dm is going to end up being the mass per unit length, the density of this object, times the length of this little piece here, which is going to be lambda dx, or lambda dl, if you want to call it that, to start with. So each little dm is going to be lambda dl, and the dl is going to be a dx. So it ends up being lambda dx and times the distance to it. Well, the distance to each one of these from the center of the rod is x, whatever distance that is, and it's going to change. So it ends up being x squared lambda dx, and that's fine. Now the rod goes from half of the rod is on the left side and half of it's on the right side of 0. So it goes from negative L over 2 to positive L over 2. So we go ahead and put those limits into our integral, and we integrate. Simple enough. So when we integrate x squared, we get x cubed over 3 times lambda, which is a constant, comes through, and then we evaluate between negative L over 2 and L over 2. We start at the top limit, L over 2 cubed, minus a minus L over 2 cubed, right? The minus goes away, then minus cubed becomes minus, and then the minus becomes positive, so we end up adding, and we end up adding an L cubed over 6 in each case, right? Or a lambda L cubed over 6 in each case, and we end up with, we also end up with an L on the, we end up with an L on the bottom when we replace lambda with the mass of the rod over the length of the rod, because that's the definition of the linear density. So then we get an L cubed divided by L times mass, and all comes out as 1/12 ml squared, which is exactly what we expected to get, because that's what showed us in the previous section. So this is just a simple example of how you calculate those. If you're doing a more complex one, then it becomes a little more messy. If you do the same thing with the 0 at the end of the rod, you get a very similar kind of integral, except now you're going between 0 and L, and when you do it between 0 and L, it becomes 1/3 ml squared. So which one of these things is going to be harder to rotate? Is it harder to rotate a rod about its center or about its end? Why do you say it's harder around the end? Besides intuition. What in the math tells you that it's harder? You're correct that by intuition, it is harder to get something spinning from the end, or keep it spinning from the end than from the middle. From the middle, you just kind of give it a little tweak and it goes woo, right? But from the end, you really have to kind of keep it going and get it swinging. But why, in the math, is this the case? Remember, this moment of inertia is kind of like the mass of rotational energy. Mass, it's harder to push something with more mass, right? Which one of these has more moment of inertia for the same mass and length? This one does, right? 1/3 is bigger than 1/12. Everything else is the same, right? So that's where it shows in the math. The last thing I want to teach you today is what's called the parallel axis theorem. And this is where we can take an object's moment of inertia about its center or about some axis that we know, and we can shift it. So what happens if you have a ball like this? I don't have my camera on. Let's see here. So here we have a ball, just a baseball, and we know how to calculate its moment of inertia if it's spinning around its center like this. But what if we want to spin it around the edge like this, so it's rolling around this? Or what if we want it to go around the sun, but we want to treat it like a ball and not a point, right? Because a ball has a much different moment of inertia than a point. What if we want to do something like this? Or let's say that we, instead of spinning a rod, instead of spinning it on its axis like this, we want to spin it around something like this. So it's going around and around. It's not a point, it's a rod. You know, so what happens if we want to do that? What happens if instead of spinning the rod around the center point like this, in this direction, we want it to spin around like this, around the center point where my finger is? Well, in all of those cases, we use what we call the parallel axis theorem. The parallel axis theorem does also come from calculus, and the end result of it is that the moment of inertia of an object that has a parallel axis, where its axis is parallel to one of its other axes of rotation that you already know, is equal to the moment of inertia of the center of around the center of mass of the object. So if you have the moment of inertia of the object doing this around this center of mass like this, you take that moment of inertia that you already know, and then you add to it the mass times the distance it is away from the center of the distance that the new center is from its center of mass, right? So what does that mean? Let's actually do this on the whiteboard really quick so you can see it. So we're going to do this one where we have the moment of inertia of the rod. The rod is going to be rotating around its center of mass like this. It's going to be going like this. And the moment of inertia of the rod was 1/12, right? ml squared. Something like that. So that's the moment of inertia around its center of mass. But instead of it rotating around its center of mass, it's actually going to rotate around this point. It's still going to have a rotation that is rotating like it was before, but it's actually going to rotate with this end pointing towards the center all the time. So it's kind of like it's still rotating about its center of mass, but we've moved its center of mass this distance d, right? We've moved its center of mass off axis. That's why it's called the parallel axis. So in other words, this was our axis of rotation before. This is our axis of rotation now, and these two things are parallel. That's why it's called the parallel axis theorem. So the moment of inertia total, or the moment of inertia, the new moment of inertia here, is this one right here, the 1/12 ml squared. But then I add on the mass of the thing again, times the d, the distance it is, squared here. So I'm shifting. What's that? Why? Well, the mathematical reasoning behind this is a calculus thing, and I don't know if they actually do the proof of it here. I don't think that they do. Well, they kind of, let's see. No. Yeah, they don't, that's not a proof of it. I don't think they do the proof of it here, and I can't remember the proof of it off the top of my head. I'd have to go back and look. But it's a calculus proof. It's a geometry, calculus of the geometry's proof. And if you're really interested, we can go look it up. If you don't want to go through it, we don't have to. Like I said, I can't remember it off the top of my head. But anyway, so the parallel axis theorem can be used. And you can use it for multiple objects as well. You don't have to have just one single object. It can be multiple objects. So you can add a bunch of them together. And just like any other moment of inertia, once you've calculated that moment of inertia that's parallel with the parallel axis theorem, you can add it to another moment of inertia. So if you have a rod sitting on a merry-go-round, and you know the moment of inertia of the merry-go-round, and then the rod is off axis to it, you can use the parallel axis theorem to calculate the moment of inertia of the rod going around and around on the merry-go-round, and then add it to the moment of inertia of the merry-go-round, if you want. Right? So, and this gets really crazy when you start doing moments of inertia in different planes. So far we've only done moments of inertia. In fact, we will only do moments of inertia in one plane in this class. But if you go on to take, there's another class in physics called dynamics, and we spend like half of a semester or more just doing this in multiple dimensions, so that you have things rotating in this dimension, this plane, this plane, this plane, all different planes. You get all kinds of crazy things going on. So anyway, they're done for today, and we will see you all next week.
Next week?
Sorry, next class tomorrow.
Say next week works fine for me too.
What's that?
Next week works fine for me too.